Greetings everybody. Welcome to the RT Hill Academy course on Open Loop Real-Time Hardware in the Loop Simulation Setup, by use of IEEE 37.118.2 protocol. Our focus in this course is to provide you with valuable hands-on experience running an open loop real-time hardware in the loop simulation by using the IEEE 37.118.2 communication protocol. So, we keep the theory part as short as possible, and will only teach you the underlying facts that are essential to understand this process. This course will have two main parts. The first part will be a quick recap on the concept of real-time hardware in the loop simulation, and the second part elaborates the use of communication protocols, in particular the IEEE 37.118.2 protocol, to set up an open loop real-time hardware in the loop simulation environment. So, let's dive into the first part of this course.
As mentioned, Part 1 of this webinar will be a quick recap on the concept of real-time hardware in the loop simulation. So, what is real-time simulation? A real-time simulation is a time domain simulation in which the independent variable, that is time, grows at the same pace as the actual time does. Let me show you an example. As you might remember, this figure shows the current flowing through our good old resistor that was simulated in MATLAB Simulink. As the figure shows, the simulation has lasted for 0.1 second or 100 milliseconds. Now, let's have a look at the actual time on the computer when this simulation was running. The actual time on the computer when the simulation started was 8:20 second, and when the simulation finished was 8:20 second. So, it took precisely 0.1 second for the computer to perform 0.1 second of simulation. Therefore, the simulation was real-time. Now, before we jump into the definition of real-time hardware in the loop, or RT Hill simulation, let's see where a real-time or an RT simulation is needed. Let's assume that you want to Skype with a UFO who lives in a different world. Not just on a different planet, but in a parallel universe where the time runs 2 times faster than it does in our world. That means, for each 1 second that passes in our world, 2 seconds pass in the world of the UFO. So, from your perspective, the UFO would look like a fast-forwarding video, whereas, from the UFO's point of view, you would look like a slow-motion video. Conversely, if the time in the UFO's world runs slower than it does in our world, then, from your perspective, the UFO would look like a slow-motion video, whereas, from the UFO's point of view, you would look like a fast-forwarding video. In either case, you would not be able to properly communicate with the UFO. That would be exactly the case when you interface an actual device with a computer simulation. In this example, the actual device, which might be, for example, a controller or a protection relay, represents you. Likewise, the computer simulation represents the UFO. The time progression for the device is ruled by the time in our world, which is the real time, whereas the time progression in the simulation is governed by the simulation engine. And that can be either faster or slower than real time. So, if we want the device to properly interact with the simulation, we should make sure that the simulation runs in real time. This is where the real-time simulation is needed. And, because the real-time simulation is interfaced with a hardware, the whole setup is called a real-time hardware in the loop, or RT Hill, simulation. You may wonder how the simulation is interfaced with the actual device. Keep in mind that a commercial-grade device is designed to interface with other actual devices in the field. For instance, the device shown in this example expects to receive electric current measurements in the level of a few amperes and voltage measurements in the level of a few hundred volts from current and voltage transformers in the field. The problem is that the analog signals provided by the real-time simulator are limited within a few volts, so a current or a voltage amplifier is needed to scale them up to the level that they becomes meaningful to the actual device. The control signals that are sent back to the simulator may or may not need an interface, depending on their magnitude. You may wonder if there is any other way to implement the interface. The answer is yes. With the advent of communication-based architectures for industrial plants, the devices in actual plants are nowadays interfaced through communication networks, rather than analog or digital signals. Therefore, the real-time simulator manufacturers have implemented a wide range of communication protocols that can be used to interface real-time simulators with the actual devices. This approach is, in fact, the interfacing method that you will learn in this course. Okay, now that we have reviewed the concept of real-time hardware in the loop simulation, it is the time to get started with the second half of this webinar, which explains the use of communication protocols, in particular the IEEE C37.118.2 protocol, to set up an open-loop real-time hardware in the loop simulation environment. Let's start with basics. What is a communication protocol? Imagine two people who are trying to communicate. In order for them to understand each other, they have to understand the same language. This requirement is independent of the physical media that they use for communication, meaning that, no matter what technology they use to communicate, they have to be able to comprehend the same language. That would be exactly the case when two devices are interfaced to communicate with each other. No matter what physical media is used, both devices should be configured to interpret a system of rules that is known to both of them for transmission of information. This system is called communication protocol. In other words, a communication protocol defines the rules, syntax, semantics and synchronization of communication, and possible error recovery methods for transmission of information. There are several communication protocols that are utilized in different industries. Real-time simulators can emulate the industry-standard communication protocols to enable the users to perform realistic real-time simulations. Our focus in this course is on the IEEE C37.118.2 protocol, that is the IEEE standard for synchrophasor data transfer for power systems. However, before jumping into this topic, let's quickly review the definition of synchrophasor and the device that produces it, which is Phasor Measurement Unit, or PMU. Let's start with the definition of phasor. As we all know, a phasor is the complex number representation of a sinusoidally varying signal. As this figure shows, the angle of the phasor, phi, depends on the point at which the signal starts at the beginning of time. The question, one might ask, is that what time is considered as the beginning of time when t is equal to 0? For example, is it the time in London, or the time in New York? Or the time in somewhere else in the world? The Coordinated Universal Time, or UTC, embedded in GPS signals, can be used to synchronize the measured electrical voltage and current waveforms. This synchronization results in synchronized phasor, or synchrophasor. This process is performed by a device, called a Phasor Measurement Unit or PMU. So, a PMU is a device that produces estimates of synchrophasor, frequency, and rate of change of frequency, from voltage and current signals, and a time synchronizing signal. The estimated quantities are time-stamped, using the precise time provided by the GPS signals, and then streamed into communication networks. The PMU functionality is embedded in most of the real-time simulators. So, they can be configured to compute the synchrophasors out of the simulated voltage and current waveforms, timestamp them, and then stream them into the communication networks. So, now that we have reviewed the definition of synchrophasor and PMU, it is the time to have a closer look at the IEEE C37.118.2 communication protocol. What is the IEEE C37.118.2 protocol? The IEEE C37.118.2 is a communication protocol that defines a method for exchange of synchrophasor measurement data between power system equipment. In other words, this protocol is the language by which the phasor measurement units, or PMUs, communicate with other devices. Each data message, complying with the IEEE C37.118.2 protocol, contains the information of the synchrophasors, system frequency, rate of change of frequency, and user-defined analog and digital values. Note that, the PMU has to be configured to select what synchrophasors, and what analog and digital values, to include in the data messages. Okay, we have discussed in the previous slides that real-time simulators such as RTDS and Opal RT can be configured to act as virtual PMUs. Now, it is the time to introduce you a couple of platforms that act as PMU clients, meaning that they can be configured to receive the PMU data that are streamed by any PMU. PMU Connection Tester. It is a Windows GUI application used to validate, test and troubleshoot connections and data streams from PMUs. In addition, it graphically visualizes the synchrophaser data in real time. OpenPDC. As implied by its name, it is a Phaser Data Concentrator, or PDC, offered by Grid Protection Alliance, that is designed to receive PMU data from multiple PMUs in real time, time-align the data, and provide it to user-defined actions as well as to custom outputs for archival. Okay, now that you know real-time simulators can be configured to act as PMUs, and you're familiar with PMU clients, you can set up an open-loop RT Hill simulation environment by use of IEEE C37.118.2 protocol. And the last word before we close this lecture. Be aware that we, at RT Hill Academy, are setting up a platform for remote access to our RT Hill simulation facility, where the course participants attain hands-on experience running RT Hill simulation. During the hands-on training session, you are supposed to complete a list of real-time hardware in the loop simulation tasks, for which you will receive all needed instructions. Your performance will be evaluated by our instructors once your hands-on training session ends. Finally, upon successful completion of your tasks during the hands-on training session, you will earn an RT Hill Academy Certificate of Completion, a proof that you have knowledge and hands-on experience on the course that you have taken. If you are interested, please sign up below to receive a notification once our platform is launched. Please note that this service will be offered for a fee.
I hope you have enjoyed our lecture on open-loop real-time HIL simulation setup by use of IEEE C37.118.2 protocol. Thank you for your attention. Take care and see you next time.